I would like to give the word over to Jørgen Christensen-Dalsgaard, who will talk from the sun to solar-like stars.
Thank you very much, Sofia. So first of all, I would really like to thank the Foundation for this very great honor that has been bestowed on all of us. And equally, for this recognition of the whole field of helio and astrocosmology. Because, of course, this is the work of hundreds of people that has developed the field over the past 50 years. And I think we all agree on that we stand here as representatives of all these people, as much as for our own individual contributions to the field. So with that, what I really want to do in this talk is partly to show how seismology is used in other fields of astrophysics, and partly to point out all the loose ends that all the young people here should work on once we are finished, which in some cases might be fairly soon. So let's start with in the sun and start with a picture that Douglas showed of the velocity field observed on the solar surface. And of course, when you observe that, you do that using a detector, like in your cell phone, a pixelated image with lots of pixels, many more than shown here, about 700,000 in the case of the MDI instrument that Douglas mentioned. And what that really corresponds to is placing 700,000 seismographs on the solar surface. So the geophysicists are really envious for us helioseismologists that we can do that. I mean, they have a few hundreds here and there and everywhere. We have an equal mesh of seismographs on the sun. And so the question is really, what do we learn from that? And so I'm going to talk first about the structure of the sun. We have the observations, they're here shown as frequencies as a function of this wave number, the degree L, that measures how many waves there are on the solar surface. And measured with a huge precision. You can see the error bars, they are 1,000 standard deviations. So we have measurements to a precision of 1 part in a million for these frequencies. And then what do? You compare that with your model, one of my models, and it looks pretty good. But of course, with 1,000 sigma error bars, the deviations are really very, very significant. And you have to carry out a detailed analysis of these differences between the observed frequencies and the model frequencies to see what's wrong with the model. And this is wrong with what's wrong with the model that I just showed. Douglas talked about showed the sound speed in the sun, and you could barely see what was going on between the model and the sun. Here what I show are the relative differences between the solar sound speeds and the model sound speeds, and again shown with error bars that you can barely see. So in one sense, this is a marvelous result. We have a model of the sun, a computed model of the sun that matches solar structure to within better than 0.5% in the square of the sound speed, and therefore in temperature. On the other hand, it's a terrible model because the differences are much, much bigger than the standard deviation. So there's something significantly wrong with the model. So this was a situation about 30 years ago. And since then it got worse. And I think Douglas alluded to that. We had new measurements of the composition of the sun, measured from the solar surface. We extrapolate from the surface composition to the composition in the interior, and use that in the model calculation. And the result of that is shown here for two of these newer models. And the AGSS09 is the most recent. And you see that what we had before at 0.5%, the differences are now up at about 2%. So things have got a lot worse. And that means there's something we don't significantly understand about the interior of the sun. Something in the physics of the interior of the sun that's wrong in our models. And this is a very active field of research, even now. We had a workshop in Switzerland last autumn discussing that. And the most likely explanation is that we don't understand atomic physics. My wife did a PhD in atomic physics and left the field, unfortunately. Otherwise, everything would have been fine. There are errors in the way our calculations of how radiation is absorbed by atoms in the solar interior, and that's something that we have to work on more. Then let me move on to a completely different aspect of the sun. Sunspots. They have been very much in the media recently because there is, this is a picture for just a couple of days ago, a huge sunspot that gave rise to a solar eruption and caused marvelous northern lights that unfortunately we slept through in Aarhus. But the sun is not always like that. Sometimes the sun shows absolutely no sunspots. And the question is why? And the variation in the number of sunspots shows a very regular pattern. It's called the butterfly diagram. What's shown on the top graph is the occurrence of sunspots as a function of latitudes on the vertical axis and time on the horizontal axis. And you see these patterns of sunspots moving from high latitudes towards the equator. And then there are periods, down here we have the number of sunspots. There are periods where there are very few sunspots. And then at the moment we are actually in a phase of an increasing number of sunspots. And we have this cycle of about 11 years. And we don't understand why. But one of the things that are almost certainly very important in that is the solar internal rotation. Douglas showed a picture of that. Let me repeat that picture. And let me also take this occasion to recall the memory of a very dear colleague and another former PhD student of Douglas, Michael Thompson, who was about 10 years younger than me, and we had a very close collaboration for many years, and very sadly he died young 6 years ago. A big loss to us and a very big loss to the field. But the point here about this diagram is precisely this change in rotation between the latitude varying rotation in the convection zone, down to this dashed line, and then the solid body rotation in the interior. And the models we have of the generation of the solar magnetic field has to do with this difference in rotation, meaning that if you have a magnetic field extending from the interior into the convection zone, it gets stretched and strengthened by the rotation difference. And that somehow conspires with convection and other aspects of rotation is the thought. It's not fully understood, but the thought is that this is actually what causes this 11-year variation in the number of sunspots. What we would really like to do would be to understand this well enough to be able to predict it. Because as you also heard, these explosions from the sun might be quite dangerous to our technological society. And therefore having a better understanding of how and when these occur would be very important. There's another relation between the rotation, the helioseismic rotation, and the sunspots. And you see that if you take an average rotation rate over time, still as a function of latitude, this is just a little bit below the surface, and subtract that average from the actual measured rotation rate. And then what you find is that there are bands of slightly more rapid rotation and slightly slower rotation moving towards the equator. And these bands move in the same way as the position of the sunspots. So there's some relation between these rotation variations and the sunspots. But we don't know which is the chicken and which is the egg. Whether the rotation controls the sunspots or whether the sunspots control the rotation. And that again is something that we need to try to understand better. Now, with this, let me move on to other stars. And here I'll talk about solar-like oscillations, oscillations like the ones we see in the sun. And we know now that in the sun, these oscillations are excited by the noise created by the convection. Here's an image of convection close to the solar limb. These hot bubbles rising and sinking with speeds close to the speed of sound. And that causes this noise that resonates with the interior of the sun and sets up the standing waves that we see as oscillations on the solar surface. And from this model, we can more or less understand the amplitudes of the oscillations we see. But more importantly, we expect that all stars that have this kind of convection, and that means all stars like the Sun or cooler than the Sun, should have similar oscillations. And so we have a chance to do this kind of analysis for a huge range of stars. Now, in the Sun, Douglas showed you the spherical harmonics. We have this huge range of different kinds of modes, thousands of them that we can observe. In stars, we just observe the star as a point. And so the only modes we observe are the ones that don't have a complicated structure on the surface. And these are the modes with the low number of waves on the surface, a low degree, basically between 0 and, I haven't shown the mode of degree 0, that's just spherically symmetric oscillations, and 3. But that, as Douglas also showed you, these low degree modes are the ones that go all the way into the core of the Sun. And therefore they tell us something about what goes on in the core also of these distant stars. And that means that we get average information about the bulk of the star, but that includes information about the structure of the core of the star, including information about how much hydrogen has been turned into helium, and therefore information about the age of stars. And age is going to be important in the rest of this talk. So what do we need to observe that? Well, we need extremely high sensitivity, because the amplitudes that we see on the surface of the Sun and Sun-like stars are velocities of the order of a few centimeters per second, maybe 10, 20 centimeters per second. And we see luminosity variations of the order of a few parts per million. So we need that very high observational precision. We prefer to have very long observations, years if we can. And we would like to have observations that are almost continuous. So how do you do that? Well, we turn to a different field of research, the search for planets around other stars. And one of the techniques used for that is to consider the case where we have a planet that in its orbit passes in front of a star. We only see the star as a point, but we still see that the planet covers a bit of the surface of the star and therefore removes a bit of the light from the star. So if we observe how much light we receive from the star, we get a dip in the light. If we have the Earth passing in front of the Sun, seen from a distant planet, the dip is only 1 part in 10,000. So we need to be able to observe that with high precision. And we want to observe that for a very long time to be sure that this is a planet coming back in front of a star. And that is precisely what we need to observe oscillations of these stars. So thanks to this study of exoplanets, we got, and Bill Borucki fought for 20 or 30 years with NASA to get this mission called Kepler, to observe these planets in this way. And Hans Kjeldsen succeeded in convincing Bill Borucki that this was such an important instrument also for astroseismology that he allowed us to get the data and use that to do astroseismology. And this has been the basis of this huge development of astroseismology since Kepler was launched. And the launch was in 2009, and it worked perfectly up to the day when the momentum wheels expired. So we have 4 years of continuous data for very many stars from Kepler. And that has allowed us to study a huge range of different stars. All these blobs show stars that show oscillations as a function of the surface temperature on a logarithmic scale. So we have 3,000 degrees here, 10,000 degrees here, and 100,000 degrees here. And then as a function of luminosity in units of the solar luminosity, so we have the solar luminosity here, much fainter stars here, and much brighter stars higher up. And the stars I'm going to be looking at here are the solar-like stars that are sort of in this range, cold enough to have this surface convection that excites the oscillations. So what we expect to get from that is what we see in the sun, a spectrum of oscillations showing the oscillation power, in velocity in this case, as a function of frequency, and with this very regular structure of peaks separated by a constant amount, other peaks in between also separated by a constant amount. And this is what we see if we observe a solar-like star, or two actually, with Kepler. And we get data that are, of course, much, much better than these very early data I showed before for the sun. In this case, for two double star, for binary star, slightly more massive than the sun, and therefore, and the frequencies are slightly lower than the frequency that we see in the sun. So these are the wonderful data that we are able to work on. And just to characterize the spectrum again, I mentioned this separation between these peaks, we call that delta nu, so that we can measure with high accuracy. And as Douglas said, the bigger the star, the lower the tones, and the smaller this frequency separation. And you can show that that scales like the square root of the mean density, the mass of the star divided by the volume of the star. The second thing we can measure is where most of the power in the oscillations is. The frequency where the power is the maximum. And for some reason that we don't understand, and that's something else that we should try to understand, that scales also with the mass and radius, but with the mass and the radius, mass divided by the radius squared. That's the surface gravity of the star. So if we can measure these two quantities, then we have two measures of mass and radius that are different, and so we can measure the mass and radius of the stars. And you might say that's boring, but masses and radii of distant stars are one of the hardest problems in astrophysics up to this point. And now we can measure masses and radii of tens of thousands of stars just from these very simple measurements. There's much more, but we'll get back to that. So let me just get back to the exoplanets, because that's one important example. Here's a planet observed by Kepler. What we see, there's a blow up here of the light curve. We see these dips. You can also see them up there, with the white dashed lines occurring with a period of about 45 days. That's one planet going around the star with a period of 45 days. But then you also see these much smaller dips with a period of 0.85 days. So this is a planet going around its star in less than a day. So if you live on that star, you have birthday about once a day, slightly better than that. And this is a star that we have observed with Kepler also to do astroseismology. And from these data, of course the data are not as good as we have for other stars, but they're good enough in an analysis done by a master student in Aarhus to get the mass of the star to slightly less than solar mass, 0.9 solar masses, the radius slightly bigger than the solar radius, and to determine the age of the star. As Douglas said, we can determine ages from looking at the oscillation frequencies. An age of 10 billion years, more than twice as old as the sun. And then we can characterize the planet. We have the data here, the dip in the light curve that gives us how big the planet is relative to the size of the star. We can also measure how the speed of the planet going in orbit around the star. That gives us a mass of the planet. And so we find that this planet has a radius of 1.5 times the radius of the Earth, a mass of 4.6 times the mass of the Earth, a mean density of 8 times water, 8 grams per cubic centimeters. And that was the first exoplanet around another star, definitely shown to be of a rocky nature. Planets found before that were huge gaseous planets. Now, of course, it's so very close to its star The age we know from the age of the star, 10 gigayears, and the surface temperature we can estimate to be about 1600 centigrades. So if you want to find another planet to move to, this is not it. And this is just one example of very many planets we can characterize in this way. Here is a more recent example showing a number of planets observed with Kepler. And you see that we have planets in the whole range of ages from about 2 billion years all the way up to almost 12 billion years. All these are planets with stars with planets around them. And you might wonder, if you have an Earth-like planet with life that is twice as old as the Earth, how life might have evolved and civilization might have evolved or killed itself in those additional 5 billion years. So astroseismology has been hugely important in the study of exoplanets by allowing us to characterize the stars that the planets orbit around. Now I want to move to stars that I actually find the most interesting of the stars that Kepler has observed. With my excuses to Connie, she's going to convince you that hotter stars are even hotter and even cooler. But red giants. A red giant is what's going to happen to the sun when it grows old. Some of us, when we grow old, grow in size and turn red. And the same is going to happen to the sun. It's going to grow hugely in size by up to a factor of 100 and get cooler and therefore redder. So to understand a bit of that, let's look at how stars evolve. Here we have a star like the sun, very schematically. There's a central hydrogen core where hydrogen is turned into helium. We call that hydrogen burning. It's a bit misleading. And when the hydrogen is used up in the core, we have a star where there's a helium core. All the hydrogen has been turned into helium. And outside that is a thin region, a shell where there's still hydrogen fusion. And then even later, the helium core heats up to the point where helium starts to fuse into carbon. And then we have a star where we have a helium fusion at the center. We still have the hydrogen shell. And then we have the outer layers of the star that really become very, very large. And this tiny helium core is not much bigger than the Earth. So that's the kind of structure that our models tell us we see in these evolved stars. And if we look at it again in this diagram where we have temperature on the horizontal axis and luminosity on the vertical axis, we see that in these initial phases, the luminosity increases a little bit. The sun is about 30% brighter now than it was when it was born. That continues for a while, and then we hit this phase where the star is cooler or redder and gets much, much, much bigger than it is now. And this is what we call the red giant branch. And then when helium ignites and stars behave sometimes opposite to what you expect, you start a new fusion process, and the star gets less luminous because of the readjustment of the structure. And then we get what we call, for astronomical reasons, the red clump. And what we have are stars actually on a red giant branch and the red clump that look very similar superficially, but are completely different on the inside. And since I should have pointed out here that in terms of the lifetime of stars, this phase that we call the main sequence, where we have the central hydrogen burning, is by far the longest part of a star's life. In the case of the sun, it's about 10 billion years. The red giant branch is only another couple of billion years, and then the later phases are even shorter. And that means that if we could measure the age if we see a red giant, its age reflects how much long time it spent in the central hydrogen burning phase. And that age time we can estimate simply by saying that the time is how much fuel we have, and that's proportional to the mass of the star, and how fast that fuel is used up That's proportional to the luminosity of the star. And it turns out that the luminosity increases very rapidly with mass to about the power 4. So the age on the main sequence scales like the mass of the star to the power -3. And that means that if we can measure the mass, and of course you know all that we can measure masses from astrocosmology of a red giant, then we know its age. So why is that important? Well, it's important because we can use that to study the Milky Way galaxy. And the reason for that is that we actually see solar-like oscillations in red giants. These are observations from a different space mission called Crafoord, showing, again, these power spectra of frequency and power for a range of red giants. And you see the frequency gets smaller and smaller as we move up. And that's simply because the radius increases. They look the same qualitatively to what we see in the Sun and other main sequence stars, and so it's the same processes going on for all these stars moving up to stars that are really very much bigger than the Sun. So what does that have to do with the Milky Way galaxy? Well, let's take a look at the picture of the Milky Way galaxy, or not quite, its twin. This is the Andromeda galaxy, the closest big galaxy to the Milky Way, but it looks more or less like the Milky Way. To look at the Milky Way, we can use the Gaia mission. And actually, Lund has played a very important role in the development of ESA's Gaia mission. And this is a picture of measurements of Gaia. Gaia has measured the properties of more than 1 billion stars in the Milky Way. The distance of the stars, how the stars move in the Milky Way. And then other observations have measured the chemical composition of these stars. And based on these data, we have the idea that the Milky Way was not created like that from the beginning. The Milky Way was created by smaller galaxies colliding and building up this huge galaxy that we see now. So this is obviously an artist's impression of one of these collisions. For some reason that I don't remember, it's called the Gaia-Enceladus sausage merger. It's probably the biggest merger. And what we see now are not a separate galaxy mixed up with the Milky Way galaxy as a clear entity, but we can see stars that move in a different way from the other stars in the Milky Way galaxy and have a different composition from most of the stars in the Milky Way galaxy. And from that we infer that these stars were formed outside the Milky Way galaxy. And then after they formed, they merged with the Milky Way galaxy. And if we do that, we identify these stars, the red giants, like that, from their motion and composition. And then, of course, from astrocosmology, we can determine the ages of these stars. And we know that these stars have to have been formed before the merger, because otherwise everything would have been mixed up if the stars were formed after the merger. And so from that, we can identify that this merger happened at most about 9 billion years ago. So we are beginning to build up the history of the Milky Way galaxy by combining astrocosmology with the Gaia observations, and this is just one of many mergers that we are beginning to identify that were altogether formed the Milky Way galaxy. So now, in my last 10 minutes, 7, I want to turn to a completely different class of waves. All we've talked about so far have been acoustic waves, sound waves. That's what you see in the Sun, that's what you see in main sequence stars. But in a gas, there are other kinds of waves, and here's an example from the Earth's atmosphere. Waves that show up because they are reflected in the pattern of the clouds. These are internal gravity waves that in some sense corresponds to the waves that you see on the surface of a lake. Except on the surface of a lake you have a discontinuity in density. Inside stars you have a gradient in density, and that still supports waves like that. And these waves we also see in other stars. So let's go back to a main sequence star, this solar-like star. We had this pattern of frequencies, the power as a function of frequency. We have this equal spacing, delta nu. We also have some fine structure, peaks quite close together. This is at degree 0 and 2, and we have, again, 0 and 2 here. And then we have degree 1 in between. And then if we look at a red giant in the same way, what we see is superficially quite similar. I mean, we have modes of degree 0 and 2, and 0 and 2. But then in between, we don't just have one modes with degree 1. We have a group of modes of degree 1. And that was identified actually by a student of Connie quite a number of years ago, to come from modes that looked like gravity waves in the deep interior of the star. And the way to see that, it turns out from theory, is that you look at the period spacing, the period difference between these modes. And when you do that for a model that matches the observations, you see these dips in period spacing. And the observations show the same dips in the period spacings in these groups of modes, of dipolar modes of degree 1. And so that demonstrates that we have this gravity wave behavior in the interior of these stars. And so you can think of that, and this actually is an image made by another student of Connie's, Peter de Grote, that you have waves that look like acoustic waves in the outer parts of the star, and then in this tiny core, not much bigger than the Earth, we have these different kinds of waves that look like internal gravity waves. And if we then go back to observations and look at two Kepler stars, red giants, they look very much the same on the surface. I mean, if you looked at them just like astronomers do, they would look the same. Slightly different temperature, more or less the same luminosity. If you look at the oscillation spectra, superficially, they also look the same. I mean, oscillation spectra are boring, just lots of peaks sticking up, and that's about all there is to it. But then if you look more carefully at these oscillation spectra, you see that in the top star, these dipolar L equals 1 group of peaks are much closer together than in the lower star. Quantitatively, the spacing is about 53 seconds in the top star and 96 seconds in the bottom star. And that, it turns out from our models, shows that the top star is just burning hydrogen in a shell around the core, helium core, and the bottom star is also burning helium in the helium core. So from these data, we are looking at a star that's 10 times as big as the Sun. We are looking at what would be, on that scale, a marble in the center of that star. And we are telling the difference between whether the star is burning just hydrogen in a shell around the helium core, or whether there's other nuclear reactions going on in the core of the star. And we can do that for many, many stars because we have observations of thousands of these red giants. So we can actually classify the stars. And here we do that in terms of these, this frequency separation of the acoustic modes and the period spacing of the mixed modes, the gravity-like modes. And the task now is to use those data in detail to understand the properties of these stars. Now, the final point, let me just mention that briefly. We can also measure rotation of these stars. We can measure the splitting that Douglas talked about in the peaks. And so we can study the rotation in all these stars. Here, the rotation of this tiny core. And what we find is, what we would expect from models is that these cores will rotate very rapidly. Here, that's shown in terms of the rotation period of the core. And the models are shown down here. And the observations are actually higher than even the most slowly rotating core rotates about 10 times faster than the models. And we don't understand why. Something must be transporting angular momentum out of the core. Could be magnetic fields. We don't know. We don't understand how that will work. And we actually do see now magnetic fields in the cores of these red giant stars. This is a very recent measurement And again, you would say, okay, just more peaks going up and down like this. But the interesting point here is, here we have one mode of degree 1. We have m equal to 0. That's the mode that has no structure around the equator. And then we have one that rotates one way and one that rotates the other way. And from rotation alone, we would expect this splitting to be uniform. So the distance between these two peaks and these two peaks should be the same. And the fact that the splitting is not uniform means that there's some other non-spherical effect in the star affecting the frequencies. And the only effect we can think about here is magnetic fields. And from that we infer that this star has an internal magnetic field of a magnitude of around 100 kilogauss. And these measurements are now being made for many red giant stars and showing that some, but not all of the red giants have internal magnetic fields. And so this is one area that we are really very much focusing on now, both to measure these fields, but then also, of course, to understand what is the effect of these fields on the evolution of stars. And 50 years ago, we thought we basically understood how stars evolve. And what we're now learning from astroseismology is that we are very, very far from a complete understanding of that. And so we need to move on. We need more data. And we are now getting, in a few years, a new space mission to observe planets and stellar oscillations, the Plato mission to be launched by ESA in late 2026. So I think, Douglas, we have to stay around a bit longer to have fun with these data. Yeah. So thank you very much for your attention.